All right, so let's go ahead and take a look at some of the information necessary to complete the 4B lab for the Doppler effect. So Doppler effect is what happens when you have a moving source of sound. The pitch will raise as it comes closer to you, and the pitch will drop off and become lower as it moves away. We're also going to work backwards from having observed the Doppler effect and see if we can find some information about the original source. So some of these important terms are in your introduction page like normal. You've got some formulas over to the side. So our normal formula we see for Doppler effect is here. But in this case, because we want to work backwards and find some of the original information, we rearrange those formulas into a couple of different formats that we'll see in a future slide. And here are those formulas. So we can find the original velocity of the source by knowing the velocity of the wave. So in this case, the velocity of the wave is the speed of sound. This is told to be 343 meters per second. Technically, that's dependent on the temperature of the air, but they're giving us this number, so that's the one we're going to use. That's why if you Google the speed of sound, you may find very slightly different numbers. Okay, then we can find the frequency of the source by, again, looking at how the frequency changes between when it's coming up to you and when it's going away. Okay, so first phase, like many of these, is just a quick video demonstration. So it's very small and hard to see from here, but there's a car that's going to be driving up and blowing its horn the whole way. And then it passes by on the other side, so now it's driving away. And the recording taken of the sound is actually laid over on a special type of graph so that we can see the frequencies of the sounds. And some questions. So you've seen enough of these before. If you weren't able to hear, if sound didn't work, or any other issue, then make your best guess as what you think might be the most reasonable. And then if you miss the question, remember that you can use the hint and try again and fix it. So these are dots. There should be only one choice. Same here. One more time. And once more. And apparently one last one. All right. And so our graph replays the sounds and then draws over intensities at different frequencies and matches that over the time of the video. Okay, so you would click start and then it would play and analyzing those sounds, seeing decibels, basically seeing the high intensity of particular sounds allows us to trace these waves. The absolute lowest one really isn't enough, well enough defined for us to be able to see. And then you can kind of see some higher ones that aren't showing up very well. So we're not going to be able to measure every different version of this sound, these different fundamental frequencies or harmonics of these frequencies, but we can get a few of them. So there's a slider here to the side, and this is something that you're going to have to do for your own. All these numbers are very slightly changed, but you're going to drag this slider up and down along the way, and then you're going to use that to try to line up with the sound wave. And then you'll estimate what that says. So you may move this up and it may say something like 0.485. Then you want to remember that these are kilohertz. And so because they are kilohertz, those are thousands of hertz. So 0.485 would turn into 485. So keep that in mind when you read these values. You're going to line up the line to find a top value here and a bottom value here, and you're eventually going to do this for all these special curves that are on this graph. It's going to ask you some questions along the way. So they really like the questions in this lab. And then, like I said, you'll measure these different frequencies for different points. You're going to get different answers than mine. I've done 3 different versions of this lab and practice and for taking notes, and I believe my numbers were different every single time. So just very carefully line up where the slider goes. You can see in the background I was checking to see where the middle might be. So I was slightly under this number and slightly above, like I was kind of between these values. But you can drag that slider up and down, line it up as well as you can along the better defined part of the curve, and then go from there. Okay, once we have those values, we can move on to phase 3, and we can use those numbers to do some calculations. So There's technically no graph on this one because we started with a graph, so we're not going to take data values and make something new. We're working backwards here, where we're using the sound graph to work backwards to find the original values. Okay, so a couple of questions here. Once you've filled in and answered this data, it's going to ask you to approximate what the velocity of the car seemed to be. And again, it should just be the closest match from what was here. Unfortunately, one of my slides got skipped when it was saved, so the work for these questions isn't shown, but I will show you to the side. Okay, so if we want to find the speed of the car, then that's going to come from the formula that we saw on the introduction page, and then also from this help section here, you can pop this up and you can find that formula again. So we had that the velocity of the source, which is the car blowing its horn, is equal to the velocity of the wave, meaning the sound wave, which is 343 meters per second, multiplied by the difference in the frequencies, so the frequency approaching minus the frequency receding over the sum of the frequencies. So the frequency approaching plus the frequency receding. So for our first example, if we were to work this one out, and I'm not going to do them all because they're very similar, and you can see the answers come out to be basically the same. But we would have the velocity of the source is unknown at first. Then we'd have 343 meters per second for the estimated speed of sound. The frequency approaching, remember, is the higher number, so the frequency rises. Basically, it's like the car brings the sound to you faster, and so it sounds like it's coming at a higher pitch. So we'd have 455 here. These are hertz because we converted from the kilohertz here, that was some decimal, into whole numbers of regular hertz, which are just barely peeking out right there. Okay, then minus 380 hertz. Remember, the top part is the difference, and then the bottom part here is the sum. So we're going to take the same numbers and we're going to add them up. The nice thing about all these units, though, because there are hertz in all four separate numbers here, and eventually the hertz all cancel. So we get just some number, basically some scaling fraction or scaling factor that multiplies by the speed of sound and then gives us the velocity of the car. Okay, and then that should give us a value very close to here, and then running through all of these, because they're near multiples of each other, they're not always perfect, but they're very close, then typically all of these numbers are very, very nearly the same answer. Okay, then we can do a similar thing for the frequency, which I will do in the white space to the side where I've got a little more room. The frequency of the source, which again is the car, is equal to twice the product of the frequencies. So the frequency approaching times the frequency receding over the sum of the frequencies. So frequency approaching plus frequency receding. For our first example, if we look through here, we're going to have 2, just because it's part of the formula. Then the frequency approaching, 455 hertz, multiplied by the frequency receding. We're going to run out of room here, so I'm not going to write hertz. They're going to cancel mostly and leave just regular hertz as an answer. So I'm going to just write the numbers part so that I have a little bit better room. All right, so on the bottom, 455 plus 380. So technically on the top, we'd have hertz times hertz, which would be hertz squared, which is kind of strange. But then you would divide by hertz on the bottom, and that's where your regular hertz come back again. Be careful when you put this in your calculator. You want to assume that there's parentheses on the bottom part of this. So either add these numbers together first or type the parentheses in a calculator so that it doesn't divide by 455 and then add the 380 in a different step. If that works out, you should get the answer that's here. Then you should be able to do it a few more times and get answers that are very nearly multiples of this one. And actually, this is a fairly short lab. So once you've done those calculations, which look a little rough, but there's not that many of them, after those, you should be basically done. So there you go. If you finish the whole thing, then you'll get a congratulation page. As I've mentioned before, if you run out of time or if you submit early or if you don't finish everything, then you get a percent complete, which would be some, number less than 100. But hopefully you're all getting them and everybody sees congratulations. And that is it.